Hi there, it's Robin. Now my friend Darren, you might actually know him if you listen to either my podcasts, Growing Up 80s, or Comfortable Place on the Couch, or there's a Growing Up 80s YouTube channel that we've done a few videos for. Anyway, my friend Darren's been programming a Commodore 64 game, and if he gets stuck, he's asking me some questions. So he's at the point in his game where he wants to display a score on the screen. He's having some trouble figuring that out. It actually is a bit of a tricky thing. So there's a number of ways of doing that, and it probably depends on your game what the best solution is. But I'm going to show you a couple today. One's easier, one's more difficult, but they have trade-offs. So as always, I'm going to fire up Turbo Macro Pro. I've explained this in previous videos, so just look back on my channel and you'll find the previous two I did, which explain a lot of the details here. I'm using my Commodore 128D in C64 mode. Most of what I'm explaining will work on any C64 assembler. This is just the one I really like using. I've explained why in past videos, just because I think using the real hardware is more interesting. That's what I'm doing here, especially for the sake of the video. If I'm doing a bigger project, I might use a cross-assembler on the PC or Mac. And there's nothing wrong with that at all. Okay, so we're not going to be making a whole game here at all. I'm just going to be focusing on displaying a score for the benefit of Darren, but I thought some of you would probably learn something out of this too. So as always, we're just going to pick a location in memory. Today we're going to choose C1000. Just the way I showed how to do some benchmarking in C64 BASIC previously, today I'm going to show the old school trick of how performance or benchmarking or profiling was done when writing assembly programs on the C64. It's a simple trick, but this is what lots of game developers and demo programmers, demo coders would do. So just like last time, we'll do our little setup here. We're just disabling all interrupts here. I'm just going to do that little jump back trick which I explained last time, to get us back into the assembler quicker. That's just loading the low byte and the high byte of this routine and putting it in the NMI vector so we can hit restore. Just watch my previous video if you want to understand why that works. It's not necessary for this program, it's just a convenient way of making my turnaround quicker while I write this program. Okay, and we're just going to do a label loop. This is going to be our main loop. That's going to run over and over again every frame. And we're going to load, it's kind of arbitrary, but say at location 200 on the screen. This is towards the bottom of the screen. I should put the loop on this line. Compare with DO12 and branch if not equal to loop. And then we're going to increase the color of the border. So this is just waiting for raster line 200. DO12 is the register that does that. Again, explained it last video. We're going to increase the border color. And then in here, semicolon is for a comment. Do operations here. And then we're going to decrease DO20. You know what? Sorry about this, guys. Loop. I'm going to go with my typical wait 1, and then down here we're going to go jump to loop. So all we've done is create an endless loop here that waits for raster line 200, does a busy loop here until the VIC2 is displaying raster line 200, then increases the border color and decreases it. And just so we have it doing something in the middle here, I'm going to load X with 0, wait 2, increase X, and branch if it's not equal to 0 to wait 2. And what this is going to do is internally count. X is going to be 0, and then it'll be increased to 1. And if it's not equal to 0, which it isn't, it'll loop back. It'll keep looping all the way until X, which is a 8-bit register, gets all the way and it wraps around. All the registers in the 6510 wrap around. Once they reach the the maximum value, which is FF in hex, or 255 in decimal, wraps around again to 0. So this is just going to waste some cycles. 2 cycles for the increase X. Branch shift not equal uses 3. That's 5 cycles times 256. 1200, 1300 cycles. Okay, so let's just run that so we get an idea what it looks like. Back arrow 3 to assemble, S to start. So you see down there on the left and the right, there's a white bar. The more CPU time that you're using, the larger that bar is going to be. And this is the trick that demo coders and game coders for years who were programming on the 64 would use to profile their code. If they weren't sure how long it was taking for a routine to run, this is what they would do. We call this raster time because as the screen is being redrawn from top to bottom, from left to right, it takes 65 CPU cycles on NTSC machine to draw out one scan line. The whole frame has somewhere around 16,000 cycles available for the CPU to generate one of the 60 frames a second that the VIC-2 draws on an NTSC machine. And we can do our trick now, hit restore, and we're back into Turbo Macro Pro. Now that I've got that set up, it's been mentioned a couple times in the comments. I haven't shown anybody how to save a file yet. So all you do to save is go back arrow and S and give it a file name, score1. And OK. And to load it back again, back arrow load, and then you would just type in that same file name. Actually, just to demonstrate that too, let's start halfway, 128, halfway through up to 256 when it wraps around. So just so you see that the raster time is smaller, you see how that white bar is now skinnier because that takes less CPU time. Now we're going to try and display that score. Down here at the bottom, we're just going to put a label, score, and then byte 00, and this assigns 2 bytes for the score, a low byte and a high byte. That gives us 16 bits, which has a maximum score of 65,535. That limitation is because this technique only allows a 16-bit value to be displayed. Now you might not be happy your score can only go up to 65,000, but that's what this first technique, that's what it does, it's easier. So we're just going to go with it for now. What we're going to do is every frame, we're going to increment, I got it, increment the score. Okay, and then we are going to load X with the low byte of score, and we're going to load A with the high byte of score, which is located at, this byte is at location score, that's a label, that's pointing to some part of RAM, C1000 something, we don't know exactly, but that's what the assembler does for us. It worries about that, so we don't have to. And then we're going to load the X register with what's in this location, and we're going to load the A register with what's in this location, and then we are going to jump to subroutine BDCD. Now this routine is built into the C64 ROM. It's part of the basic routine that will print out a number like a line number. By the way, line numbers can only go up to a maximum of about 65,000 as well. I think it's actually 63,999 or something like that strange. This routine, we're kind of hijacking this routine. I don't know if it was meant to be user accessible or not. Well, the designers probably didn't care, but that's what we're going to use it for. Now I'll just go ahead and run this and we'll see what it does. And then we're going to fix it up a bit. So this has a couple mistakes here. But just for the sake of explaining it step by step, we're going to do this, and let's see what it does. Okay, so you can see that the screen is filling up with numbers. That's because there's several problems here. But you see it's generally working, and you see that it's actually using a lot of raster time. So here, I'm going to hit restore. First thing I'm going to do is start the raster time at 100 instead. I was just guessing at 200. That's too low down the screen for us to see how much raster there is. It's actually wrapping around this routine so inefficient. That's one of the problems with this routine. But we're going to just work with it for now. And another problem is that the screen was full of garbage and that the score is moving all over the screen. So actually what we want to do instead is move the cursor before we print the score up to the top left of the screen. So up here, I'm just going to do same as I did last time. Load A with 147, which is the clear screen, and jump to subroutine FFD2, which prints a character. And then what I'm going to do in here is I won't clear the screen before we print the number every time. That's actually fairly inefficient, or it is quite inefficient to clear the whole screen every time we want to print the score. And I actually don't know what is the code for home 19. We're going to go load A with 19, jump to subroutine FFD2, and then down here, print score. I'm just going to leave that commented. Back arrow 3, and start. Now let's see what it does. Okay, it's printing the score up in the top corner. It still has a number of problems. You can see it's glitching. It's using lots of raster time. It's using thousands of cycles to print that number up in the top corner. Plus, it's even having trouble. It's wrapping around. It's coming up to 255, but then when it prints a single digit, it's not doing any leading spaces before it. It's filled with problems, and it's only going up to 255. So let's deal with some more of these problems. One problem here is that I am only increasing score. Instead, let's do the math properly here. I'm only incrementing it. So instead, we're going to clear carry. That's a special flag in the 6510. Well, it has a number of uses, but one of the main ones is when you're doing addition. If you're trying to add two 8-bit numbers together, you will often end up with a 9-bit value. Just like in decimal, if you've got some 2-digit numbers like 99 and 99, and you add them together, you end up with a 3-digit value. You have a carry. When you're performing arithmetic, you'll use that carry and write down a 1 in front of the 98. Hexadecimal or binary, it's the same thing. When you add numbers together, sometimes you require an extra digit to represent the result. So that's what the carry bit is for in the processor. And we're going to load score, the low byte of score, add with carry 1, and we're going to store that back into score. The 6510 doesn't have just an add instruction, it only has an add with carry, which adds, in this case, we're adding 1, but if carry is set, we're actually adding 2. And then what we have to do is, in case there was an overflow, or in case carry was set, we have to deal with the high byte. So load A with score plus 1. This is the high byte of our score. And we're just going to add 0. But if carry is set, this is equal to 1. And we're going to store that in score plus 1. Okay, so that's kind of tedious. So yes, it does take 7 instructions to add a 16-bit number together, but we love it. Okay, so let's look at the result of this. Okay, so now watch that score go up. And as long as it's increasing, we don't have to worry about the spacing problem. It is a little weird that it's left justified, but I don't think we're going to solve that today. This video is going to take forever if we try to deal with every detail. But I think you can see from the raster time that you shouldn't be devoting a whole, like more than half the screen of your raster time per frame just to displaying your score. It's extremely inefficient, and it just doesn't work for games. There's so many other things, more important things for a game. Sam's Journey, you saw how much amazing work it was doing when I was talking about that some episodes ago, how much it's doing per frame. It's incredible, and you can't deal with inefficient routine like this. So anyway, this BDCD routine, that might be fine for basic. It's not good enough for us. So how do we speed this up? Okay, so I'm just going to go back to basic so I can just show this on the screen. If you got a regular hexadecimal number, by the way, on the 6510, it's common. We put a $sign in front of a number to indicate that it is hexadecimal. And so FF is the maximum 8-bit value that you can have, which is equal to 255 in decimal. Sometimes we put a plus sign in front to show that's decimal in the Super Snapshot Monitor, for example. And that's also equal to binary. We often use a percent sign to indicate binary. 1, 2, 3, 4, 5, 6, 7, 8. All three of those things are equal to each other. And the reason we call this an 8-bit processor is that the registers in the CPU can only handle a maximum number like that. And then so for a 16-bit value, that's the same as FFFF. If you combine 2 bytes together, you can do a bigger value like we were just doing. That's equal to 65535, which is equal to 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So those are the maximum values available with 16 bits. The 6510 has a different mode that can use for addition and subtraction called BCD, which is binary coded decimal. And this was actually a fairly advanced feature at the time in a little processor like this. And how it works is that the hexadecimal value looks just like a decimal value. The maximum value when you're in BCD in a hex byte is 99. And that is equal to 99 decimal. So if you try to use values like AA, which is a valid hexadecimal mode, if you're in BCD mode or in decimal mode, AA is not valid. So you can have, 11 is fine, and that equals 11 in decimal, and so on. Basically, it's a slightly inefficient mode, but it has big advantages. So each nibble is 4 bits. Basically, binary code decimal is packing 2 decimal values into the accumulator at once. The disadvantage is it's a little less efficient. You're not making maximum use of all the bits you have, but it's much easier to deal with decimal numbers, such as to print them out. Converting from hexadecimal to decimal is quite expensive. So if your program is wanting to display decimal numbers to the user, as you do for the score in a game, this is a lot more efficient way of dealing with it. Making slightly less efficient use of a few bytes saves loads of cycles. Okay, just a brief intermission here. It's actually been almost a week since I recorded the first half of the video. I tried to continue on with the next part, but it was getting really sprawling. So I took a bit of time to plan out what I was doing next rather than just winging it. And I hope the rest of the video will make more sense as a result of that. So also if the camera angle or the lighting looks a little different, that's why. And also I took this computer with me to the library earlier this week. I'm trying to start up a retro computer club here in Thunder Bay, Canada. I'd encourage any of you, if this sounds like an interesting idea, try to get one started in your city. It really doesn't take much. I found one of the local libraries allows you to book a room with a good-sized table in it, and there's power there. I just needed to bring some extension cords. I brought my 128D, a PET, an SX64. I put out the word on Facebook, and we ended up having about 10 of us there. It was a lot of fun. If you're going to do it, it'd be great if you knew of at least one other person that you get along with. If the two of you agree, let's do this, then you're bound to have a good time. Of course, you may even want to have it in your own house or whatever, but you might have concerns about inviting people over. Possibly strangers are going to show up and you don't know, might not know what you're getting into. But anyway, Thunder Bay Retro Computer Club, a successful first meeting. And I also wanted to say that previous method of showing the score I showed just minutes ago, I think I said that wasn't suitable for games. I really should clarify that. It's entirely suitable for some games. It's very easy to use, and if you've got a slower paced game, it's probably perfectly adequate for that. I even used that myself in my minigame Splat forum for the score. It's not updated while the screen is scrolling, but when you die or are about to begin a new level, it prints out the score using that routine. And my little role-playing game, Minima Reloaded, that also uses that same BDCD routine. Okay, just a little bit more about this BCD. You type in here on the blank screen. If you've got 19 hex and you're in regular hex mode and you add 1 to it, then that is equal to 1A. And you keep adding plus, if we added 5, then that would equal 1F. And it's not till you add one more that then it would be equal to 20, to 20. Okay, so that's in regular mode. But if you set decimal mode, that's the opcode for it, then 19 plus 1 equals 20 hex. So that's what's special about BCD mode, is again, it treats these numbers as if they really are decimal. Each nibble, which could have 16 possible values, only has the first 10 being valid. And then the addition, the ADC, opcode, the add with carry, or the subtract with carry, both of those are the only ones affected by decimal mode. If you were using an increment, opcode would treat that 19, if you incremented it, it would change it to 1A. So it only operates in hexadecimal mode. It's only add and subtract that work in decimal mode. Okay, to continue on with where we left off. So I saved a new file just to get the state of the machine back to where we left off last time. Some of it was lost during my failed attempts to do this. So one thing I just wanted to quickly do is show one possible optimization. And instead of doing all this code just to add 0 with a carry of 1, what we can do instead is get rid of these lines. That's, by the way, back arrow and delete, deletes a line. And then we can test if carry is clear, then jump ahead and otherwise increase score plus 1, ahead 1. Okay, and so this does exactly the same thing. You load the score, you add 1 to the value and store it. Now, if carry is still clear, then you're done. There's nothing to do with the high byte of score. But if carry is set, we increment the high byte of score. I just wanted to show that you actually can't use this optimization when you're doing BCD math. I need to point that out now. So now to use the BCD version, the first thing we have to do is start treating score like it's a BCD value. It's a decimal value. I'll try and just say decimal now instead of BCD. So we're going to go down to score, and we weren't happy, I wasn't happy with that limit with the previous version of only a 16-bit value. Now with decimal, it won't be a 16-bit value anymore. It'll be a 4-digit value, which is even less. That's a maximum score of 9999. Now, most games, it's pretty typical to have a limit of 999,999, at least 6 digits in your score display. So we're going to add one extra 0 here. So it's now using 3 bytes. Inside each byte is 2 decimal digits. The low byte is score. The middle byte is score plus 1. That's the location it is in memory. And the highest byte is score plus 2. Now note that the 6510 processor puts the low bytes at the beginning, typically, and we'll keep with that tradition. We don't absolutely have to do that. The most significant digits are stored here on the right, but they're going to be printed at the left when we're displaying the score. Okay, and now that we have this value, you don't have to do anything else to the score. It's just bytes like normal. Do operations here. We still have our benchmarking to increase the border to see how much more efficient this is going to be in raster time. So it's very simple. You just go SED, set decimal mode. That turns on BCD mode. Then we go ahead and do our addition. And those lines I just erased, I'm going to put them back here. This only handles 2 bytes. Now we have 3 bytes worth for the highest 2 digits. So it's just keep extending the pattern. Load score with 2, add carry 0, store A, and score +2. Okay, so now we are incrementing the score by 1 every frame. Now we can throw out this old code that would set up for the print of the score. Okay, and what we have to do, now that we're done our decimal arithmetic, we have to clear decimal mode. Clear is the same as off. And then we're going to do one more thing here. JSR, that's jump to subroutine display. And just to keep our code tidier, that's all we're going to do in this section. And we're going to now write the routine we still have here where we decrement the border color back to black. And we jump to done. Okay, so here under the score, we're going to just put the label display. That's the name of this subroutine. And we're going to set up our index registers. Y, we're going to set to 5. We're going to be using the Y register to indicate what position in the score we're showing. And we're going to start at the end, the rightmost value. We're counting from 0 here. So for example, if we want to show a score of 0, 1, 2, 3, 4, 5, this is position. I've made the score match the position. So this is position 0, 1, 2, 3, 4, and 5. It matches the score. Of course, we could be doing this for any score like 999999. I would still number them 0, 1, 2, 3, 4, and 5. So that's what Y is pointing to. We're going to start at the right-hand side and draw our score left. And we're going to load X with 0. So I'm going to just put a comment here after the semicolon. Screen offset. And here, this is the score byte index. So as we work our way through score here, we're going to start with the low byte and move to the right. And now we're going to do S loop, stands for score loop. And we're going to load in our score, the low byte of the score, with index X. So right now X is 0, so it's going to load in this low byte, which initially is a 0. So we've loaded the score in, and we're going to need this number for later. So we're just going to push a copy of it onto the stack. Push A onto the stack, and that's just going to save it for later because we'll need it again. And then we're going to AND the accumulator with 0F. Now the AND operator does a logical AND. 0F will cause the higher nibble to be zeroed out, but it will keep whatever is in the low nibble. That's the lowest digit in our score, 0 through 9, and this is going to keep it. And then we're going to jump to another subroutine called plot digit, which is actually going to display the score. Now we have in the accumulator, after this AND, we have the lowest digit. So let's just start a new subroutine, plot digit. We have to fill in this part later, but for now we're just going to map this out. So what do we need to do with plot digit? We have a number from 0 to 9, but to show it on the screen, we actually have to show the screen code for the number 0 or more. And look here, this is in the Programmer's Reference Guide, Appendix B. The number 0 has a screen code of 48. Unfortunately, they start at 0 and go up. So you can just simply add whatever digit 0 through 9 to 48 and end up with the correct screen code. I think some computers might actually have 1 through 9 and then 0 at the end. And of course that would make the logic more complicated, but fortunately this is the sane way of arranging it. So we have to add 48 to the value we've passed into this routine. So as always, we clear our carry before we begin an addition, unless we have a very good reason not to. We're going to add with carry the value 48. You put a number sign in front to indicate that it is a literal 48 and not location 48. And we're going to store that to screen memory, comma, Y. As you remember up here, Y is the screen offset. So it's going to be the rightmost digit. We're going to store on the screen. We actually haven't defined screen yet. I'm going to use F1 to jump up to the top of the file. to the top of our source. And right under jump back here, I'm going to go screen equals 400. And that's the default screen memory in the Commodore 64. Maybe in a future episode we'll move that somewhere else, but for now we're just going to go with the default. F7 to jump back down to the bottom of our program. And then we're going to decrease Y. Since we've plotted a digit, we're going to move that Y index to the left one position, and then we're going to return from our subroutine. So that goes back up here. The program flow goes back up here. Now we'll continue our program. By the way, I like to put blank lines whenever it feels like kind of like a paragraph or a thought has been completed in assembly language. So this is these 4 lines, plus the subroutine down here, have printed the low digit in that byte. Now we're going to pull A to pull back score that we had fetched here, and we had pushed on the stack here. We're pulling it back into the accumulator so we can retrieve the high digit in the high nibble. And how do we do that? We pull it in, and then we do a shift right. And we do 4 of them to move the high nibble down into the low nibble. And I'll probably put a diagram up in the top corner that attempts to make that more clear. But when you have a byte of memory, you can shift the bits inside the accumulator left or right. Of course, if you shift them left, some will spill out the left end or likewise out the right end, and they actually spill out into the carry. Move all the bits left, and that's like multiplying them by 2, or you can shift them to the right, which is like dividing them by 2. We're dividing by 2 4 times in a row, which is the same as dividing by 16, which is a way of getting the high nibble down into the low nibble so we can work with it. Okay, now our high digit is down in the low digit position. We can simply jump back to that plot digit routine we wrote, and it'll print out the next character. And again, it will advance the display output one more position to the left, getting ready for the next one. Okay, so we printed out 2 digits. Now let's loop so we can do it again. We're going to increase X, which is going to move to the next score byte, the middle score byte. And we're going to compare, just in case we're done, do we now equal 3? We have bytes 0, 1, and 2, we've numbered them. If we're at 3 now, if X is now at 3, then we're done. If we're not, we'll branch, if it's not equal, back to S loop, which is up here, to do it again. And if it is done, then we're simply going to return from the subroutine back up to here and end the operation. So that's it. Let's see if it works. Back arrow 3 to build, and we're going to hit S to start. And there we go. It's counting up. So we already know it's handling up to 3 digits. And while it goes, check out that raster time. If you remember the previous way of doing it, it was using up basically almost a whole, not quite the whole screen, but it was using about 2/3 of our raster time per frame. This routine is using, I don't know, what is that one? Maybe about 5 raster lines instead of maybe 150 or 200. And this is actually displaying 6 digits worth of score, while the previous one could only handle not even a full 5. It was up to about 65,000. We'll show you one more thing here. Instead of increasing the score by 1 at a time, we could increase it by 10 at a time, like this. Or we could even do 100 at a time. So what I'm going to do is add 1 in the middle digit. So it's actually equal to 100 at a time. Let's go ahead and try that. There you go. Very quickly there, we're now testing that the highest digits work as well. Okay, or we could add like 99 99, and we'll see how that goes. I'm going to assume that that is working fine. Okay, and back to this here. Yeah, notice that 0 in decimal or 00 in hex, those are all the same values. Just depends on the context which you should use to make your code more readable, to imply so that you can show your intent better. So I did just want to point out how that increment optimization I did earlier in hexadecimal mode does not work in decimal mode. There is an optimization you can do, but because increment doesn't work in decimal mode, all you can really do is go, if carry is clear, to say we'll call it done 1, and down here we'll put the done 1 label. So if carry is clear, there's nothing more to do. You don't have to update the middle and high bytes at all. So you can just branch away to done. And likewise, carry is still clear after the middle byte, then you can branch to done 1. But this is one of those cases which often happens where you can optimize for speed. That's what we've done here. Or you can optimize for size. A lot of the time you get to choose. Do you want it to be faster to run, or do you want it to use less bytes? Sometimes you can get both, but there's a lot of times where you can only get one or the other, and you have to choose what's more important. Okay, that's it. If you're still finding these useful, please let me know. Appreciate it if you like the video, subscribe to the channel if you haven't already. If you know anybody else that might be interested in what I'm trying to do here, then please do let them know. And I appreciate all the support. We just hit 600 subscribers. Thanks again. Have a great day. We'll see you next time.